BJT, JFET, and Op-Amp. It's my intention today to do a quick review of the first two topics, diodes and BJT. I'll be asking you questions to test your understanding. So I'll go through a lot of students on the list. I think, have 2 or 3 more classes before the midterm, which will be in the next year. So we can do other reviews at that time. I haven't looked at your quiz papers yet, but I received responses from all the students who took the quiz. 38 responses I received in total. I am planning to check and grade within this weekend, or it will take me 1 more week because it takes some time for that many students. I'll open my screen to share with you. We'll go to the topic of chapter 1 and 2, semiconductor diodes, which is the building block for this course. I hope you can see that on the screen. First, we learned about a diode, which is a 2-terminal device, ideally conducting only in one direction. What is the name of the plus terminal of the diode? What do we call the plus terminal of the diode?
Anode.
It is called the anode. Well, and what about the minus terminal?
Cathode.
Cathode. Yes. How do you create a diode like this? A basic diode, how would you create a diode? If I give you some material, how would you build a diode? Take 2 materials, make a diode. What will you do? Phil, Mr. Phil Liktawa, do you know how do you create a diode physically?
Creating a PNP junction. A PN junction.
PN.
PN.
So what is P, what is N? These are 2 different types of semiconductor material. What do you call a pure semiconductor material which has not been subject to any impurity? There is a name for it, a semiconductor material which you did not dope or did not inject any sort of impurity. What is that called? How about I ask Martin? Is Martin here? Martin? Michelle, is Michelle here?
Yes, Ajahn.
What do you call a semiconductor material which is completely in the purest form? No impurities. What do you call that one? Does anyone remember?
Silicon.
No, that's the name of one of the materials. A semiconductor material which has not undergone any impurity is called intrinsic. After you dope, you can either create a p-type or an n-type. What do you call a doped semiconductor material? Is Pichayut here?
Yes.
What do you call a doped semiconductor material, Pichayut? Extrinsic material. It's not on the slide, but I taught you. If you go back to the recording, I'm sure you'll find it. So there are conduction regions and non-conduction regions of a diode. There are 3 types of diode biasing. What are those biases? We salute.
Not sure, Abjan.
Okay, let me ask Napatra. What are the three different biases for the diode?
Reverse bias
Mhm.
and like forward bias,
Yes.
and the last one I can't remember.
Last one, you can say no bias,
No.
means you don't do anything.
Okay.
You do not connect, it's called no bias. If you connect in forward, plus minus is forward bias. If you change the polarity, it's reverse, and then the third one is no bias. So once you connect in forward bias, the diode will conduct current. Ideally, diode is represented by a closed switch or a short circuit. So the diode voltage drop across is zero, unless I mention silicon, germanium, or gallium arsenide. They have their own voltage drops. Silicon, for example, 0.7 volts. Once you have a short circuit equivalent, you have infinity current, which is shown on this vertical blue line. This is using the ideal diode. When you reverse bias, the diode is like an open circuit. An open circuit doesn't conduct current, so you have no current. But what happens in reality, let's say you take a silicon diode, when you apply forward bias, you need about 0.6 to 0.7 volt for the current to start flowing. And when you reverse bias the diode, the current is not exactly zero. There is a little amount of current, usually in micro, nano, or picoampere range. We call it the reverse saturation current. This is the periodic table of elements. Here it is shown silicon, germanium. You can also even find arsenic, gallium, etc. So the doping means taking a semiconductor material and adding impurities. If you add foreign material, it is called impurity. By doping, you can create p-type or n-type. What about the n-type? On the n-type, if you look at the outside balanced electrons, there is one extra electron which does not create bond. So because of that free electron, the net charge of n-type material is negative charge. On the other hand, during the creation of p-type material, there's one lack of electron, which we also call the hole. This lack of electron creates the opposite effect with the net charge plus. So when you take the p material and n-type, you join, you get the p-n junction, which is our basic diode. N is minus net charge, p is plus net charge. When they join each other, the opposite charges attract. The positive ones migrate to the negative side, and the negative ones migrate over to the positive side. As a result, the terminal of P becomes minus and the terminal of N becomes plus. I am here drawing a distinction between the material inside and the terminal outside. At the PN junction, we have a region in the middle. We call it the depletion region. In the depletion region, you have both electrons and holes, but they do not participate in conduction of electricity. If you see minus and plus circled, these are the depletion region charges which do not participate in electricity. But you'll also see in materials N and P type, you have both electrons and holes which are not covered by the white or black circle. These are the free carriers which will participate in the flow of current. What happens to the depletion region when you forward bias a PN junction? I'll ask Sesihan.
Yes, then.
In the forward bias condition, How big or how small is the depletion region?
They're both equal.
They're both equal. What about the reverse bias? If you reverse bias, what happens to the depletion region?
Stays the same.
I'm afraid it is not the right answer. When you join P and N, in the middle there is always a depletion region. And if you forward bias, the size of depletion region is moderate. But when you reverse bias, the depletion region becomes wider. You can think of the depletion region as a wall which the free electrons and holes have to overcome in order to conduct electricity. So we asked about these three operating conditions: no bias, reverse, and forward bias. No bias means you don't apply any external voltage. So there is no current flow, there is no voltage drop. That is quite obvious. In the no bias, the depletion region is quite minimal. When you reverse bias, means you put the minus polarity of your battery or DC on the anode and plus polarity on the cathode, you have an equivalent circuit of open circuit. So very wide depletion region. But there's a reverse current flowing, reverse saturation current, because of the concept of majority minority carriers. My next question will be for number 1.
Yes.
What is the majority carrier in the N-type material? There are two types of carriers, electrons and holes. For the N-type material, which are the majority carriers? Do you know the answer?
I'm not sure.
The majority carriers in the N-type material will be electrons. So what are the minority in the N-type? Holes. In the reverse bias, we have a wide depletion region, and in the reverse bias, the minority carrier has more opportunity to flow. The little bit of saturation current in the reverse bias is due to the flow of minority carriers from one side of the junction to the other side. Sometimes you may think that P-type has only hole and N-type has only electron. That is not true. Both types have both holes and electrons, but in one type of material, either hole or electron, they dominate. But both P and N types, they contain, you see from the diagram, both of them have holes and electrons. One is just more than the other. The normal operating condition of a diode is forward bias. When you do plus and minus polarity, a regular diode current ID will flow forward. The voltage drop across the diode is VD. For silicon, 0.7 volt VD. Germanium is 0.3, gallium arsenide 1.2 volts. If in your exam or any problem, the diode material is not specified, you can assume ideal diode, which is VD equals 0 volts. So what happens in the forward bias? A lot of majority current will flow. Minority current will not have too much chance to flow, but they will flow in the opposite direction. The total diode current is majority subtract the minority. The main current is usually in milliampere and the saturation current is in microampere. When you take milliampere minus microampere, the final answer doesn't change that much. So it's almost the same. In the forward bias, there is enough potential energy for the electrons and holes to cross through this depletion region, which I said you can imagine like a wall or a barrier. This is the characteristic of a silicon diode. As you can see, nothing happens until about 0.3 volts. After 0.3 volts of forward bias, a little bit of current is showing up, and at 0.7 you have full amount of diode current. In the reverse bias, you see it's picoampere, 10 power negative 12, and the forward bias is milliampere. There is really no comparison. But it does not mean that the diode can handle infinity current. There is a maximum forward current rating for the diode, which you will find from the spec sheet. If you exceed that rating, you will damage. So here is the concept of majority and minority carriers. There are two currents through the diode, majority current and minority current. Here it says which type of materials are majority and which types are minority. There's one region in the reverse bias condition, we call it the Zener region. You can keep adding minus voltage until there's a point. If you reach that point and you exceed that point, there will be a lot of reverse current. Actually, the diode is breaking down. We call this region the Zener region. The maximum reverse voltage, the limit that will not take the diode into the breakdown region, we call PIV, or peak inverse voltage. Let me ask another question. Kritsanapong,
Yes, teacher.
can you apply as much reverse voltage as you want to a diode?
This one I think so. No, I'm not sure about it.
Let me ask you the question again and listen carefully. You want to add reverse voltage to a diode. Can you just add as much as you want?
We cannot add more than.
More than which one? You cannot add more than what? You cannot add more than the peak inverse voltage.
Yeah, the peak. Sorry.
That is the
I-
limit. And where can you find this information, the peak inverse voltage information? What is the best way of finding it?
In the Zener region.
Yeah, but where can you find the value of PIV for a diode?
Oh,
Spec sheet.
spec what?
Yes, the data sheet or the spec sheet.
Oh,
These are the forward bias voltages. Each type of diode needs at least about this amount in order for fully conduction. When they can fully conduct, when the electrons and holes, they have enough energy to cross the depletion region. And this energy comes from external voltage. So that's why voltage is also known as potential difference. The potential or this is the electric potential energy. If you increase the temperature, the operating temperature, already the electrons and holes are energized, so they may need a little bit less in this case. See, temperature increases, it adds energy to the diode, so it will reduce the required forward bias voltage. Instead of 0.7 volt, maybe at 0.6 volt, the silicon is already conducting when you have an elevated temperature. Compared to silicon, the germanium diodes are more sensitive to temperature variations. So silicon is a widely established material for this. Gallium arsenide, they're suitable for high-speed, high-switching application. That does not mean that silicon is outdated. Silicon is still used. Different types of resistances for the diode. You can read about it, static and dynamic resistance. So for the DC mode, the static resistance is given by Ohm's law, forward voltage divided by forward current. For dynamic or AC resistance, it is given by this equation, 26 millivolt over ID plus RB. RB is the body resistance of the diode, the resistance of the material through which it is constructed, and it's very small. Sometimes you can even neglect it. 0.1 ohm to a few ohms. What is dynamic resistance in reverse bias will be infinity, because in the reverse bias it's like an open circuit. You can also find AC resistance by averaging. Maybe draw a tangent to the curve and take the two extremes of your slope, divide delta VD by delta ID. There are 4 points, 2 points for VD, 2 points for ID. You can find the average AC resistance. Oftentimes, you are asked to draw equivalent circuit. So if you are given a diode, this is what the equivalent circuit looks like. Inside you have a battery symbol with 0.7. R average is the diode's internal body resistance, which is very small. And ideal diode symbol is like that. A triangle with its peak to the right, and you have a vertical line. Is there a battery inside the diode? Why do we have a battery symbol? Natapok?
Yes.
Why is there a battery symbol inside this equivalent circuit? Is there a battery inside the diode?
I think it's battery.
You have a battery inside the diode? The symbol
Yes.
is the DC battery. Is he right? How can you have a battery inside the diode?
I don't sure, Ajahn.
The battery symbol just representing the voltage drop when the diode
Ajahn,
is
no
forward
battery.
biased.
No battery.
There is no battery. How can you put a battery? The diode is already small. It is just representing the voltage drop, nothing else. Sometimes you have to represent with symbols. Capacitance. There are two plates in a capacitor. One is positively charged, one is negatively charged. In between, non-conducting. In the reverse bias case, you have a large depletion region, so the gap is wide. This creates a capacitance effect. If you are forward biased, there is still a capacitance effect, but it is different. Reverse recovery time. This is an important concept you should study. When you switch the diode from forward bias to reverse bias, what do you ideally expect for the current flow? Let me ask Kolawik. Kolawik,
Yes.
when you switch the diode from forward bias to reverse bias, what current do you ideally expect?
Uh,
What is your expected current from forward bias to reverse bias?
minus 100.
That is what you expect when you change the bias? What about you, Piladon? Is Piladon here?
Yes, yes.
What do you expect the current to be when you change the state from forward bias to reverse bias? Satawat,
Yes.
what current do you expect from changing the state from forward bias to reverse bias? What current do you expect?
0.
Zero current. Reverse bias should not be any current. But what happens in reality? There's a little bit of reverse current. Why is that? That's what you need to read about the majority and minority. When you reverse bias, the minority carriers, they flow, so they take some time to become the majority state in their oppositely charged materials. During that time, there is a current flow, and then that current level will drop down, and then finally you will have zero. Reverse recovery time then is the time the diode requires to stop conducting when switched from forward to reverse bias. For a high frequency, high speed application, we need a very small reverse recovery time in the switching circuit. This data can be found on the spec sheet. So here's an example of a slide what you can find on the spec sheet. You want to check the diode, you can check with the diode checker, ohm meter, and curve tracer. Make sure the forward voltages are what you will expect from each type of diode. An ohm meter, depending on how you put the black and red probe, it will show high or low resistance. If you have a curve tracer in the lab, it will show you the characteristic graph as long as the diode is working properly. We have other types of diode, Zener, LED, diode array, which is a combination of many diodes. A Zener diode has a special symbol. It is connected in reverse polarity, cathode and anode, but once it starts conducting, when you read or calculate the voltage, you still have to take plus minus, not minus plus. Zener diode. What is the other name of Zener diode? There is another common name of a Zener diode. Rajay, let me ask Rajay.
Yes, Ajahn.
Can you tell me another common name of Zener diode?
Ajahn, I don't know, Ajahn.
What about Seni?
Me too, Ajahn. I don't know.
Have you ever heard of voltage regulators? I talked about it in the class. A Zener diode, also sometimes called a voltage regulator diode, because the voltage across a Zener diode is fixed. Once you turn on a Zener diode, it provides a fixed voltage, and the same voltage appears across the load. That's why it is called a voltage regulator. The second chapter, LED. LED has a special symbol, as you can see. There are two curved arrows. Once the LED has enough voltage for forward biasing, what happens? You will have the light on. There are so many different types of LEDs that you can find. So there is no fixed color. You can have red, white, blue, orange, so many of them. Usually 2 to 3 volts forward bias is required for LED. Sometimes the LED is on, but you don't see anything, especially for the remote. It gives you an infrared light. The human eye cannot see all light waves. It can see only certain bands. After that band, it cannot see. Before that band, it cannot see. So sometimes the light is visible. The other times the light is not visible. An array is this when you have so many diodes connected together in order to create an IC package. You can have all anodes joined together. We call the common anode, and the cathodes are independent input or output. Similarly, you can have all the cathodes joined together. We call it the common cathode connection, and then you will have similar, you have independent anode output or input. The second chapter talks about some very common applications of diode. What did we study as a common application? Half wave rectifier, full wave rectifier. You had what else? AND gate, OR gate. I taught you AND gate and OR gate, I remember. Clipper and clamper circuit. So in order to solve any diode or amplifier circuit problem, the load line analysis is very important technique. You see the blue curve. What is that blue curve? That is the diode characteristic curve. It is the character. And then you have a straight line taken at two extremes of voltage and current. This one is called what? What is this called? The load line. Where does it come from? Balang. Is Balang here? Seems that he's not here. Miss Pichayapon.
Yes, sir.
From where do you get this black load line?
Decided by the network.
Decided by the network, and what does it mean by the network? What is the meaning of network in this case? The network means the circuit. The circuit that is around the diode is the network. So from the network you can find the two extreme points. When the current is zero, what is the voltage? And when the voltage is zero, what is the current? You add these 2 points, you get the load line. When the load line intersects the characteristic curve, what do we call that point? Pakon?
Yes, sir.
What do you call the point where the load line joins the characteristic curve? How about Nataya?
Yes.
What do you call the point where the load line joins the characteristic graph? What is the name of that point? There is a name for that point. What is the name? Do you remember the name? It is called the Q point or the operating point. You find the operating voltage and operating current based on the Q point. Given circuit, if you change the circuit configuration, the operating point will change. I'm not going to go through these derivations again. you can read, but one of the first examples we studied for diode application is half-wave rectifier. When an AC waveform is an input to a diode circuit, there are two parts of AC, positive part and negative peak, positive peak and negative peak. So what happens during the positive peak? During the positive peak, if you connect like this, what is the bias condition of the diode? Forward or reverse? In this half-wave rectifier that is shown to you, what is the biasing condition for the positive peak?
Forward bias.
Forward bias. Will the diode conduct electricity in forward bias? Will the diode conduct current? Yes. So that's why you see an output. What happens when the input cycle is a negative half peak? What is the status of the diode? Which bias?
Reverse bias.
Reverse bias. So in the reverse bias, the ideal diode is like an open circuit. No current, you see there is no peak in the second half cycle. If you want to have full wave rectification, how do we do that? The thing you have to be careful about is when you apply the AC voltage, it has a peak, right? Plus Vm or minus Vm. For the plus, maybe not too much worry, but on the negative peak, it goes to a maximum value of minus Vm. You know there is a limit, peak inverse voltage. If the peak of the input signal exceeds, if the negative peak of the input signal goes beyond the peak inverse voltage, you will damage the diode. So this is one of the issues you have to worry about, and you have to design accordingly. For a full wave rectifier, you have an input, positive and negative peak of an AC wave, and then the output, you see half peak for both half cycles. There are DC levels associated with both half wave and full wave rectifier. And there are formulas. I think these appear on the formula sheet. How can you create full wave rectifier? You have to use either 4 diodes or 2 diodes. The first example was 4 diodes in a bridge configuration. On the positive half cycle, only 2 of the diodes are on. In this example, diode D2 and D3 are on. You'll get the first half output. On the negative half cycle, D4 and D1 are on, the other 2 are off, but you still have a full path of conduction. Then you have the other half peak. Is it possible to make a full wave rectifier using only 2 diodes? Let me ask someone. Komchan,
Yes, sir.
do you think you can make a full wave rectifier using only 2 diodes, not 4, just 2?
It's possible, sir.
It is possible. There's a name for it. What do you call that? Center tap transformer.
Sorry, sir.
Center tap is like this.
Tap. Oh, I see. Yeah, I remember that. Okay.
This one is one of the full wave rectifiers where you need only 2 diodes, not 4.
Okay, sir. Thank you.
The secondary side of the transformer, when you tap at the center, you create 2 half cycles there. So you can have full wave rectification without using 4 diodes. This is an important slide on your screen now, the different formulas, ideal versus realistic diode, the DC levels. For the value that you get on the output side, it looks like the peak of the C wave. It has a peak and valley, but actually it's a DC because it is not changing direction with respect to the 0 point. We have a clipper. If you connect input and diode and then a load, you can see if the input has positive and negative peaks. On the positive half cycle, it conducts. On the negative half cycle, it does not conduct. So it cuts or clips away any part of the input voltage that does not forward bias it. This is the clipper. It's a series clipper. We have bias clippers. If you want to change the level of shifting, if you want to shift the level of clipping, you can add any DC inside. You can have parallel clippers. Instead of connecting the diode in series with the input, you can connect in parallel with the input. In this case, during the positive half cycle, the ideal diode is 0. During the negative half cycle, the ideal diode is an open circuit. You are just sensing the negative input voltage through the outer loop. That's why for a parallel clipper, it clips away the voltage which does forward bias. There's a summary slide of what the output will look like for clippers, and also the next one is called clamper. What is a clamper? A clamper clamps or shifts the DC level, an AC signal to a specific DC level. The analysis of clamper circuit is not straightforward like clipper. First, you have to see what are involved. After the input, you have a capacitor, then you have a diode, and you have a load. First of all, you have to decide during which half cycle the diode is conducting. And then you do the KVL loop analysis, find the output voltage, also find the polarity of the capacitor, voltage and polarity of the capacitor. Then you go to the next half cycle where the diode is not conducting. In this half cycle, you have to have whatever voltage you found in the conducting cycle for the capacitor, voltage and polarity. In the second half cycle, you have to maintain the same voltage and polarity for the capacitor. Then determine the output voltage. Lastly, you have to compare the output with the input and make sure the total voltage swing compared with the output and input, they are exactly the same. Then you have arrived at a proper solution. We did a few examples in the class. A clipper and clamper, okay. The clamper, you can also have a bias clamper, but the DC biasing you have to apply in the same branch where you have the diode, in series with the diode. Do not put in another branch. We have Zener diode as the last application. Actually, not the last, because I showed you AND OR gates in the class. But for the Zener diode, it's a diode that conducts when it's reverse biased. So given here is a typical Zener diode circuit. First, you have to determine whether the Zener is on or off. So let me ask Waramet. Mr. Waramet.
Yes.
When you try to determine whether the Zener will be on or off, what will you do first? What is your first step in the circuit?
Put the I'm not sure. I think
You have to think that the Zener is not in the circuit. Zener diode is not in the circuit, so you have to determine VL. How are you going to determine the load voltage VL? Using what formula? Using what formula?
I forgot the name of formula, but
Can you tell the formula?
um
Who can tell the formula? What is VL equal to? If the Zener is not in the circuit, what is the equation for VL in this circuit? Phil, can you tell?
This is KVL, right?
Okay, somewhat related, but there's a specific name. Okay, what is the VL? You don't know the voltage of any other points. You only know input voltage, and you know the resistor.
Oh, a voltage divider.
That will be the voltage divider equation. V across RL will be VI times RL divided by R plus RL. Find this value of VL and then compare with the Zener voltage rating. It is given in the circuit or in the problem. If VL same or greater than VZ, the Zener will be on. Then let's say the Zener rating is 8 volt, VL is 9 volt by calculation. So when 9 must be greater than 8, so when you find this, the Zener is on, and then VL will be same as the Zener voltage, not 9 volt. VL will be locked to the value of Zener voltage. Because once it is on, it locks the voltage, and the parallel voltages should be the same. But if you found through calculation that VL is 6 and VZ rating is 8, the Zener is not on. So this Zener branch is like an open circuit. You solve only for the outer loop. There are maximum and minimum values of RL which will keep the Zener on. Maximum RL, you have minimum load current. Minimum RL, you have maximum load current. But when you think about maximum and minimum load current, you also have to be careful about the Zener current rating, because it can handle only a maximum amount of Zener current. Zener is a very important topic that you should review well. And also there is an input range. VI, you can have a minimum VI and maximum VI, which will keep the Zener operating as normal. So you can change RL, you can change VI. If you want to change the Zener output level, you have to get another Zener diode, because the rating is kind of fixed. This was a quick review of the diode application chapter. The next one I intend to talk about today is a review of the BJT, bipolar junction transistor. Which is chapter, there are 3 chapters concerned with BJT, 3, 4, and 5. We talked about the PN junction. For BJT, it's a 3-terminal device. So there are 2 junctions. You can either have PNP or NPN. 3 names of the terminals: base, emitter, and collector. You can have a PNP BJT or an NPN. The symbols are different. As you can see in this case, you have a PNP BJT. The emitter base junction is forward biased. The collector base junction is actually reverse biased. If I zoom in, you see there's a thin black vertical line and there's a wide black vertical line. What do they represent? What are they representing?
The depletion region between the P and N junctions.
Yes. Why the PN junction is thin and the NP junction is wide? I already told you, I already gave you the answer actually before. PN junction here is forward biased and NP junction is reverse biased. When you reverse bias, the depletion region gets quite large. That is the reason. And then through the PN junction, you have a majority current flow, which is given by the wide and thick blue arrow. NP junction is reverse bias, so the minority carriers will flow, and some small minority carriers can go to the base. There are three currents: base, emitter, and collector current. IC is the collector current. It is given by beta times IB. The total current, emitter current, is always IC plus IB. Whether you have PNP or NPN, it doesn't matter. This law does not change. When you change the type of transistor, you just reverse the polarity and current direction. Typically, IC in milliamp, IB in microamp. So sometimes you ignore microamp in the equation. We oftentimes write IE approximately same as IC. That is possible. You can have three types of configuration for the BJT: common emitter, common base, and common collector. Throughout the course, we used mostly NPN and common emitter examples. In a common emitter, the emitter terminal is grounded. It is common to both the input side, which is the base, and the output side, which is the collector. And you are seeing the symbol of BJT. This is an NPN BJT because the arrow is going out of the body at the emitter terminal. If the arrow is going inside the body at the emitter terminal, that is PNP, and all the current directions will be changed. IE equals IB plus IC. It is also following the Kirchhoff's junction rule or the Kirchhoff's current rule, which says the current going out equals the current coming in at a junction. These are the other configurations. You have two characteristics. You have the graph on the right hand side and you have graph on the left hand side. Then let me ask you this to Sukaina. Sukaina, are you here?
Yes.
Which one is the input graph and which one is the output graph? On this slide, which one is the input side graph? Which one is the output side graph? You can take some time to see and analyze the information given to you.
Is it IB?
IB is which one? Input or output?
Output?
No, IB is not the output. IB is the input base current. For a common emitter, the input is base. The input is always base, no matter how you configure it. In this case, the output is collector. So it's not the right answer. But why do we need two graphs for this device? In the diode, you have only one graph. Why do we need two sets of graphs? This question I'll be asking to Warapat.
Yes, sir.
Why do we need two graphs in order to describe the BGT?
Because like one is for the current and one for like the voltage. Is that what you're looking for?
No, that's not the exact answer though. Even you can have one graph, you can still see current and voltage. When you have three terminal devices, you need two sets of graph. The diode is only two terminal. You can easily establish input-output relationship with one graph. When you have two terminal devices, you need to have three terminal devices. When you need to have two graphs. So one graph is not enough. There are three operating regions for BJT: active, cutoff, and saturation. Active means the normal operating range. In the cutoff, you can have a lot of output voltage between collector and emitter, but little current or no current. The saturation is opposite of cutoff. You have a lot of current, the transistor is on, but little or no voltage. Here are the approximations we use for BJT. I see approximately IE. In some of the problems, you can use it to simplify. The voltage drop from base to emitter, we always take as 0.7 because we are assuming silicon BJTs. There's a ratio alpha. IC over IE is called alpha. Ideally, it should be 1. In reality, it should be 0.998 or 0.9. Beta is a very important one. It is an amplification factor. Beta relationship can be established between beta and alpha. Beta is alpha divided by 1 minus alpha. And IC equals beta IB always. The BJT, is it a voltage control device or a current control device? Voltage or current? What is it controlled by?
What did you ask? Can you please repeat again?
Is the BJT a current control device or a voltage control device? What is the controlling parameter of the BJT? Can you answer? It's a current control device. In case you forgot, which is very obvious. So here is the operating region example. The white region is active region. The left vertical blue region is cutoff, saturation, and the bottom region is cutoff. The BJT also has, just like any other device, the BJT has maximum power rating. So you have to make sure that the product of output current and output voltage should not become more than the input, more than the PZ max. Here in this example, 300 milliwatts. Some examples of a BJT spec sheet. After we talked about the basic construction, the next one is DC biasing. Biasing means adding DC source or DC voltages to a transistor in order to turn it on so that it can amplify signal. Signal means AC. Any transistor cannot amplify a signal by itself. It has to have some source to turn it on. Also, the amplification happens due to energy transfer, power transfer. The average power of an AC signal is 0. So you need that DC for that. There are regions, we already talked about this, but we studied 4 types of biasing circuit: fixed bias, emitter stabilized, voltage divider, and collector feedback, which is in this slide, they named DC bias with feedback. For a fixed bias, you have base, collector, resistor, no emitter. The input and output are coupled using capacitors. When you do the DC analysis, how should you treat the capacitor in the circuit? This question will be for Sirin.
Yes, teacher.
During the DC analysis, how do we see the capacitor in the circuit? How should you treat it?
We should ignore it.
When you ignore it, it is an open circuit or a closed circuit?
Open circuit.
It's an open circuit. The current through the capacitor IC equals C dV over dt, but V is not, in the case of DC voltage, V is not changing with time, so it's a constant, and then d dx of a constant is 0. No current means it's an open circuit. For any DC analysis, we should definitely ignore the capacitor and ignore the AC signal. You just concern yourself with the DC. And then there are 2 loops, inner loop and outer loop. When you solve the loop, you have the loop equation. You have to find base current. After base current, you can find collector current. And for the load line, you can take the outer loop and you find the load line equation. Then you can find the Q point. Some of these problems, they have to be solved graphically. If you change the VCC, the Q point will shift left. If you change the resistor, the Q point will also shift left as long as you have the same base current. But if you change the base current, the Q point will shift from one IB to the other IB because the base current now is changing. When you add an emitter resistor, the circuit becomes more stabilized because beta is something that changes with temperature. When beta changes, the output can change a lot. The output voltage and output current both can change. You don't want that to happen. When you add the emitter resistor, the output will still change, but not as much. That's why emitter bias is more stabilized than the fixed bias. You can make it even more stable by using 4 resistors. I'm gonna go to the voltage divider. R1, R2, RC, and RE. This one is even more stable. If you have a voltage divider bias, there are 2 ways of solving the problem. First is called the exact analysis using Thevenin. The other one is called the approximate analysis. If you do the exact analysis, you have to spend some time to find the base current and then find the rest of the information. All the formulas here are given on this sheet, which you will see in the exam. But if you do the approximate analysis, you don't have to find the base current. You can find VE, IE, etc., and then you can calculate backwards, saving some time. You cannot always use the approximate analysis. Beta RE must be greater than R2 in order to do the approximate analysis. For the exact, you have to find Thevenin voltage, Thevenin resistor. This is the equation of IB for Thevenin. And then once you find IB, you can find IC, you can find the rest of the parameters by circuit analysis. For approximate, the midpoint between R1 and R2 called VB. Then you can have IE equals VE over RE. VE is VB minus VBE. Then you will find collector current. If you divide collector current by beta, you can even find the base current approximately. But when the condition is not satisfied and you try to do approximate analysis, your answers will be wrong and will not be acceptable. This is called the collector feedback. The collector terminal is fed back to the base using a resistor. And the operating point is only a little bit dependent on beta, so it's the most stable one. Output doesn't change as much with beta. Again, using the loop equation, you can find the base current, also the collector current. We did an example like this. This is called an inverter. When the input is high, the output is low, and when the input is low, the output is high. Between 0 and 5 volt, if you convert this to a Boolean or digital logic, 0 volt represents a digital low, and 5 volt can represent a digital high or 1. In some examples, instead of beta, you will see H sub FE. This is same as the beta. This is also true for some type of spec sheets. You can use transistor to create logic gates, AND gate, OR gate, etc. Switching time, we just explained a little bit about this one. The time it takes to reach the 90% of the maximum output, we call this what time? The rising time. And from 90% to 10% of the output, we call it the fall time. We have something called storage time as well. There's nothing to solve here. Troubleshooting, just you can read. If you are given a PNP, which is unlikely, you just do the opposite for NPN. Change the direction for current and voltage polarity. The rest is all the same. The graph will be mirror images. After DC analysis, we talked about AC analysis using model. I mentioned 3 models in the class: RE, small RE model, hybrid equivalent, and hybrid pi, which is not shown on the slide, but I talked about it. Hybrid pi is for high frequency applications. For the RE model, we use the following circuit to approximate the behavior of the BJT when it is subject to an AC signal and in AC mode. On the input side, there's an equivalent resistance beta times small RE. And the formula for small RE is 26 millivolt divided by IE. Where is IE? IE is not given. You have to determine IE from the DC analysis. First, you do the DC analysis, find IE, and then you can find RE. To find IE, first you need to find IB. After IB, you can find IC, and then you can find IE equals IC plus IB. So multiple steps are involved. On the output side, there's an output impedance equivalent, small RO, and then a current source symbol, beta IB, because IC equals beta IB. But if you take the voltage here is plus and minus on the bottom, the current should be going clockwise, but IC is going counterclockwise, which tells you that between the input and output of BJT, there's a 180-degree phase shift. When you do an AC analysis, what will you do? First, the main circuit is given to you. I'll show you just one example. For the AC, how will you treat the capacitor when you are in the AC analysis mode? How should you treat a capacitor in the AC modeling or AC analysis part?
Short circuit.
Short circuit, yes. The capacitor is a short circuit or a closed switch. And there is one other thing we have to worry about. That is the DC source, the DC bias. What do we do to the DC source? What will you do to the DC source? You have to kill. What is the meaning of killing a DC source?
Grounding.
Grounding, shorting, grounding. So VCC will go to the ground through RB, as you can see. RC will go to ground on the output side, which is correct. Capacitor is short, and you, instead of the BJT symbol, you just throw the model inside, the RE model. In the RE model, you have beta RE and the current source and output impedance RO. Now, if you look at the circuit as a whole, the input and output impedance value you can see. From the input side, it is RB parallel beta RE, that's ZI. The output impedance Z out will be RC parallel RO. In some cases, you can ignore the small ones. If RE greater than or equal 10 times beta small RE, you can ignore the RB. For the output impedance, if small RO greater than or equal to 10 times RC, you can ignore the small RO and just say the output impedance is Z out. There's a current gain equation as well. For BJT, you have both voltage gain and current gain equation. For JFET, you don't have current gain because it's undefined. JFET is a high input impedance amplifier. The input current is 0. We don't do output current versus input current. Have voltage divider, you do the same. Short the capacitor, kill the DC source. Here is one interesting thing. For common emitter and voltage divider, there can be a bypass capacitor with the emitter resistor. If you short it, the resistor will also be shorted out. This is a shorting effect. That's why on the output side, you don't have an RE resistor. This is something you have to be mindful of. There's one example which is unbypassed RE. So the equation becomes a bit different, the circuit becomes a bit different. See, impedance calculation is different. I rarely ask this, but this is something that you have to be mindful of. Cascaded system, what does it mean? It means that you have multiple stages of amplifier. The output of one stage is acting as the input of the next stage. If you have multi-stage amplifier, the total gain is the product of individual gain. So A1 times A2 times A3. When you do the DC analysis, each stage has to be calculated separately because capacitor is open. That's why the DC calculations are independent of the cascading effect. However, when you join the circuits and do the AC calculation, capacitor is short, closed switch. Therefore, the AC calculation for gain and impedance, they are interdependent. You cannot ignore it. An example of two amplifiers in a cascade. Q1, Q2, both are voltage divider bias. C2 for Q1 is the output capacitor, coupling capacitor. It is going as the input of the second amplifier's base. When you do DC analysis, capacitors are open. You do independently for AC. Each one affects the other one. And a cascade is a common emitter, common base connection. This arrangement is used to provide high input impedance, but it results in a low gain. Why so? High input impedance is useful for canceling out any noise on the input side. This one we studied in quite depth. Please study it again. Darlington. When two BJTs are connected like this, the emitter of the first one is the base of the second one. We call it the Darlington. The total beta is beta 1 times beta 2. So the current is multiplied by a lot. It's a high current gain amplifier. Also provides high input impedance. There are equations for Darlington circuits, IB equation. And once you find IB, you can look at the circuit and find IC, IE, VE, etc. You can just use Ohm's law or KVL. Told you about the current mirror. Two BJTs are connected in a mirror-like fashion. Opposite flip version of each other. They're identical. VBE is the same. The base current will be the same. And on the input side, you have a resistor which you can change. The symbol is not given. If you change the resistor, the input current IX changes, which will also change the output current I. So the output current is a function of the input current. We call this the current mirror circuit. I get you a detailed explanation of how it works. You lower the input current, the output current is lowered. You lower the output current. If you increase the input current, the output current is increased. It is VCC minus VBE divided by Rx is the value of Ix. I think you had assignment problem, right? Current mirror. Did you receive the third assignment?
Yes, sir. We already received it.
When is the due date? Let me see. When was the due date? I can't remember. Was it in January?
January 4.
Yes,
January 4.
January 4.
January 4. Yes, that's your due date for homework assignment 3. That should also help you for getting the concept for JFET and op-amp. Midterm, it includes the op-amp. Current source circuit, if you connect a Zener diode, which is voltage regulator, and in this fashion, there's a fixed current flowing through the loop. By that, you can provide a fixed current to the rest of your circuit. It is simply VZ minus VBE divided by RE. That's the IE, and IE equals IC approximately. VBE is fixed, 0.7. VZ is a fixed for a fixed model. RE is fixed, so your current is fixed. That's the end of reviewing for BJT. We will meet next year for the rest of the review. I would now like to take your attendance by calling out your names. Balang, not present. Thiravut,
Yes.
Napatra,
Yes.
Pakon. Mr. Pakon, is he here? Rajay,
Yes, Ajahn, I'm here.
Jonikan,
yes ค่ะอาจารย์
Michelle,
yes อาจารย์
Phil is here, Silicon,
Yes, teacher.
We salute.
Yes.
Eugene.
Yes, teacher. Yes. You can.
Sisihang.
Yes, Ajahn.
Patampong. Gongsu.
Yes, sir.
Martin.
Yes, Ajahn.
Kolawik. Where is Kolawik? Pichayut.
วิเชยุทธ here ครับ
Jimma.
Yes, sir, I'm here.
Sonyuan.
Yes.
Satawat.
Yes.
Yapeng.
Yes.
Seni.
Yes, present.
Siripop.
Yes, sir.
B2. B2. Is B2 here? San An. Mr. San An. I don't see this B2. I don't see. Is not present. And I don't see Mr. San An today. Okay, absent. Waramet is here.
Yes.
Nabawan.
Here.
Natapop.
Yes.
Warapat.
Yes, I'm here.
Present, sir.
Naptaya.
Yes.
Pichayapong.
Yes, sir.
Komchan.
Yes, Komchan here.
Pilaton.
Yes, I'm here.
Kitsanapong.
Yes, I'm here, teacher.
Atit.
Yes, I'm here.
Tasin.
Yes, teacher.
Sukaina.
Yes.
Sirin.
Yes, teacher.
Min Luin O. Absent. Min Luin O is absent. All right.
Teacher,
You,
we can't
yes.
hear. I
Who?
forgot to turn on microphone.
Who is this?
Gone.
Pakong.
Yes.
อาจารย์ครับปอผมalso here.
Patompong is here, I saw. See you next year.
Thank you,
Is
sir.
Kolawik here?
Thank you, Ajahn.
Is Kolawik here? He's not responding.